Thank you, Rak. So first, I would like to start by thanking Rak and the entire team of local organizers for putting together this wonderful meeting. It's a great pleasure. They did tremendous work, and I hope that it will be appreciated within the community. And also, I hope that now this bridge between Ulsan and Beijing will be a road that will travel many times, that will go with this team to Beijing, that will come again to Ulsan, to UNIST, and hopefully this will be beginning of a long-lasting collaboration between the two centers. It's also my great honor to be here, and privilege and benefit of being the last speaker is that I can now start quoting some of the previous quotes. So to quote Bong Liang, I think I owe a lot to Professor Yao. So first I'll say a few words about how much I do and how much I appreciate everything he has done for us and for me personally. I first met Professor Yao when I was 20 years old, just basically a kid. And since then, he stayed in my life, and I, to some extent, stayed in his. He was officially my mentor, though, only for a short period of time when I was postdoc at Harvard. So he was my postdoctoral mentor. And if you measure our kind of collaboration by number of papers, then probably it's indeed maximized during that period of time. But I think his mentorship definitely did not diminish since I left that postdoctoral position. In fact, probably some of the most valuable advice I received was years after, so throughout the rest of my life and through the rest of my career. And there are many things I've learned from Professor Yao. That includes multitasking, that includes wearing multiple hats, for example, wearing mathematician's hat and administrator's hat at the same time and retaining the ability to function. So that's valuable quantity. And many other qualities too. So I lost my father rather early in my life, unfortunately, and academically, I feel that Professor Yao fulfilled to me that role of guiding me and being sort of that kind of mentor where I feel if I get ever in trouble, there would be someone to come and pull me out of that trouble. I actually don't know if that ever happened, if he had to do this for me. You can ask him. I hope not, at least not in any serious instances, but it certainly feels that way, that he would be that kind of safety net, and I very much appreciate it. So there are several valuable lessons, which again, I learned, and the way Professor Yao taught me these lessons is not by lecturing or giving a very clear set of guidance, but rather through example. And that's, of course, the best way to teach. I'm not going to discuss all of them, but one particular aspect that I learned I want to elaborate a little bit on, something that I value a lot and which will be relevant to the rest of the talk. When Professor Yao met me first, I was a very strange kid. I wanted purposefully to have one foot in physics and one foot in mathematics, and that was very intentional. So in particular, I wanted to make sure I have 2 degrees and many of my future positions will be sort of equally balanced. I'm not sure I maintain this balance. So Professor Cheng yesterday mentioned that Professor Yao could be viewed as a mechanism that as an input takes a physicist and turns that physicist into a mathematician. So it made me think that maybe that actually did happen to me to some extent, because in the past, I don't know, 5 or 10 years, I was definitely more in the mathematics side, but nevertheless, I still like to think of myself as or at least partly physicist, so I hope I retain that qualification. But anyway, going back to those early days, I felt very adamant about sort of having one foot in one field, another foot in another field. And that's actually difficult. And the way our system is set up, this is highly discouraged, because even if you prove really good theorems, the little bit of physics that you do will be played against you, as some of you probably may know, and vice versa. If you're even a good physicist, but once you talk to mathematicians, you immediately consider to be much more abstract, and basically that's in some sense, it's a double whammy. So I'm not going to go into how challenging it is, not to mention that you also have to master both subjects at the same time. But Professor Yao probably is the very first validation of this being okay. And it's kind of interesting because when the entire system is set up in one way, but you find a mentor who not only says that it's okay to be non-binary in this classification, that's really cool. That's super exciting. Moreover, Professor Yao not only encouraged me to basically keep foot in one subject or another subject, not only he said it's okay through his actions, but he actually taught me how to do this. So Professor Sean yesterday at the dinner mentioned that Professor Yao is very broad. And I want to make this remark to yet another level, because to be broad, one has to be actually brave. One has to go and have this courage to step into the unknown. And it's much, much easier to be specialized. But having this courage to cross boundaries, to build new bridges, to go to new disciplines, that actually takes courage. And these days, I learn machine learning, for example, and Rak, our organizer, knows this very well. And it's challenging and it's scary. It's basically, I feel like a student. But this is something I learned from Professor Yao. And of course, all of us who know him well would definitely vouch for this, that he has this curiosity and, more importantly, courage to not worry about not knowing something, because it's a barrier that we can easily cross. We can just learn and then master this yet another subject, go from one area of mathematics to another area of mathematics. So this is the main theme of my talk. I'll be talking about building bridges, and this is one of the important skills that I'm very grateful for Professor Yao for teaching me that. And to all the young people in the audience, I want to have this advice that just watch Professor Yao in action and always stay curious. Never stop learning. This is the slide that I actually used in some of the past talks. So by now, based on everything I said so far, it's probably not surprising to you that some words of wisdom that I received throughout my early career I like to incorporate on the slides, and no surprise that Professor Yao features on some of the slides quite a bit. So before coming here, I went through some of my past talks and looked if there are any interesting quotes I can pull out. So it turns out there are quite a few. So this is one of them. I don't know if Professor Yao remembers when and how he said it. I actually don't know myself, so it shows that it's been a while. But so this is actual slide from yet another talk. But because the slide includes this bridges and building bridges, it definitely, the context of this quote is that it doesn't matter to whether we think about this gadget as gadget and analysis or in algebraic geometry, or maybe even in physics. What matters is how well we understand it. So that was obviously the context for this quote. Again, I don't remember on which occasion he said it, but I remember kind of a snapshot of him saying that. And this is what we're going to discuss. In particular, also yesterday at the dinner, Professor Yao was asked to recall some of his most beloved or favorite theorems. Of course, it's hard to name your favorite child, but one thing he is quite known for is proof of Poincare conjecture, which is, again, bridge of this type. So it's an interesting statement that relates geometry on the one hand. So it makes a claim about existence of a metric on certain type of manifolds just from topological conditions. So this is a bridge between topology and geometry. That's the theorem. So this slide also illustrates that physicists like this because it's a solution to Einstein equations and so on. They love Calabi-Yau threefold. But to me, it's this nature of the statement of this theorem as a bridge between two different disciplines that will be motivating and again useful in the rest of the talk. So in the same way, I'll present to you some bridges today. Some of them will be quite surprising, but I think I wouldn't be crossing this, transcending these boundaries between different disciplines within mathematics and even beyond, if not for Professor Yau. So another bridge of a similar kind between geometry and topology is a problem that still is up for grabs. So hopefully some of us, including the young people in the audience, will be solving it one day. This involves basically telling how well we understand spheres, and what looks like a sphere is actually a sphere. So this goes back to late 50s, where some progress in this area was made, and importance of different topological categories or different categories was emphasized. So in the smooth category versus piecewise linear versus continuous or topological, things may look slightly different. And this was understood reasonably well in high dimension. And in low dimension, things are just simple enough that it is easier to understand. But if you picture this graph with dimension on horizontal axis, then somewhere around dimension 4, things break in a pretty bad way. So if you picture complexity, then you should probably picture that there is 1/x or even worse type explosion happening. There is a huge singularity in dimension 4, where there are lots of things which we still don't understand, and don't understand in a very bad way. So the famous Poincare conjecture, which originally stated in dimension 3, says that what looks like a sphere is a sphere, and that was indeed famously proved about 20 years ago. But in that case, we did expect the statement to be correct. We did expect the conjecture to be true. We were just waiting for carefully written proof to be available. What's interesting in dimension 4, we actually don't know whether it's true or not. So based on our current understanding of exotic structures and exotic spheres, analogous to Milnor spheres in dimension 7, in dimension 4, we don't know what should be true. So I can give you a long list of arguments why smooth Poincare conjecture in dimension 4 should be true, but I can also give you an equally long list of arguments why smooth Poincare conjecture in dimension 4 should be false. And in my opinion, this is actually one of the most exciting things in mathematics where we actually don't know. And we will, hopefully, in a very short time. And maybe one of you will be discovering the answer, whether it's true or false. But to me, it's quite exciting that at this point in early 2024, we have no clue. And at some point, hopefully not in too distant future, we will know this. So what the slide also illustrates is that there is an easy strategy or easy to state strategy to disprove Poincare conjecture in dimension 4 if you want to falsify it. So of course, it's very hard to think or visualize mentally exotica in higher dimensions greater than 3. And here we're talking about 4-dimensional spaces. So problem is usually reduced to something that we can visualize. For example, some Kirby diagrams, or which is pretty much the same structures described with knots. So these are objects in 3-dimensional space, and these are easier to visualize and work with. And that's actually what low-dimensional topologists typically use to encode the structures of, say, 4 manifolds, if that's our goal. So this theorem says that if you can find a pair of knots which share one property, I'll explain what this is in a second, and have 2 other properties, one of which it has answered yes to certain yes or no question, and the other has answer no to certain yes or no question, then that's it. You go home, you disproved very famous long-standing conjecture. What's interesting about this theorem and about the state of affairs, and in particular maybe partly illustrates what I said before, that it's hard to know whether the conjecture is true or false, is that here the theorem has three conditions. And it's incredibly easy to find situations, instances, many such knots or pairs of knots which satisfy 2 out of 3. So in fact, like I said, every knot is has this property, which I'll explain in a second, yes or no kind of property. So it's either yes or no. So that's basically very easy for a single knot. And again, I'll show that this is not a big mystery, and therefore finding pairs looks like just a search problem. So that's, again, very easy to state, but of course the devil is in satisfying all the three conditions at a time. And so far, we have actually no good clue or reason why it either can be satisfied or cannot. So I'll tell you what we do understand. So, but this is one of the big ambitious goals that it would be good to solve, or what the rest of the talk is aiming for. So when we're working on something, it's always good to have North Star guiding us, and for purposes of this talk, this could be topology side of the story. And then the main part will be on the geometric side. So I have to unpack several terms that went into definition of the theorem. So one of the conditions said that two knots should share zero surgery. And surgery is basically a way of constructing a three-dimensional manifold, a three-dimensional space out of knots, starting with a three-dimensional sphere, removing the neighborhood, tubular neighborhood of the knot, and gluing it back. And to glue it back, you have to specify how you put it back. And that's described by rational number, which is usually called surgery coefficient, here denoted by P over R. So famous theorem of Likaric-Wallace says that you can get any three-manifold by this operation of removing and gluing back. So that's what we like to do in topology, in geometry, cut and glue. We do it all the time. So this is not too surprising. The only remark I want to make about the slide is that in the world of all surgeries, not everybody is equal. So there are two special points if you think about this kind of projective circle being the line of surgery coefficients. Then point 0 and infinity are special. Infinity is a very boring surgery which doesn't do anything, because the same tubular neighborhood that you remove, you put back in exactly the same way. So it returns back a three-sphere if you start from a three-sphere. So that's not really an interesting surgery. But zero surgery is an interesting one. It's in some sense most opposite. And this plays a very important role in low-dimensional topology. For example, various versions of so-called property R conjecture, proved by Gabay and many other interesting statements, are specific to the zero surgery. Okay. By the way, if you have any questions at any point, feel free to interrupt, ask, raise hand. So then I have to explain yet another property that was stated in this previous theorem. So there was a notion of knots being either slice or not slice. So that's a yes or no criterion. And slice means the following. It means that if you think about a knot in a three-dimensional sphere and view a three-dimensional sphere as a boundary of the four-dimensional ball, then slice means that there exists a smoothly embedded disk in the four-ball, which is bounded by the knot. So that's the notion of slice. If it does exist, we call the knot slice. If it does not exist, we call it not slice. Okay. So this is my poor illustration taken from the web of the situation. Of course, it's hard to illustrate four-dimensional spaces for, again, same reasons I mentioned a moment ago. But if this is a knot and this represents a bulk of the four-dimensional ball, then you can picture that this is a disk. Yet another interesting conjecture in low-dimensional topology, since we're talking about the slice disks, is a so-called slice ribbon conjecture, and it basically says the following. So I told you what slice is. A ribbon is a stronger version. It basically says that you can find a slice disk which has no maxima. So this thing is, this maximum would be absent for a truly ribbon knot. And it's clear from the definition, since ribbon is a stronger condition, that every ribbon knot is slice, but Ralph Fox in 1962 conjectured that the converse is also true. And since then, this is being known as a famous Fox's slice ribbon conjecture, which, just like smooth Poincare conjecture in dimension 4, is something we have no idea whether it's true or false. And again, this is the coolest thing in math conjectures, where we don't know which way the story is going to go. So there are many reasons to believe that it's true, many reasons to believe it's false. But to low-dimensional topologists, both questions, the smooth Poincare conjecture as well as the slice ribbon conjecture, are equally exciting. So we like to know the answer. So here is a paper from about 10 years ago by Gukov, Charleman, and Thompson, which proposed infinite family of potential counterexamples to the slice ribbon conjecture. So in fact, this is just a picture taken from their paper. Figure 2 shows the simplest candidate in this infinite family of potential counterexamples, which, as the caption of the figure says, could be not ribbon. So it's a slice knot, but it may or may not be ribbon. So challenges to find whether it is. This slide illustrates, again, even if I didn't unpack all the topological definitions, several things that I briefly mentioned. For example, I mentioned property R. This is one of the generalizations that's part of the title of the paper. And again, it mentions this notion of sliceness, which is useful for both Poincare conjecture and this slice ribbon conjecture. Again, they propose lots of potential counterexamples. This is the simplest non-trivial one. And what's interesting, it has almost 50 crossings. So this guy, okay. So therefore, to answer these questions and where the real challenge is, we have to work with knots which have a large number of crossings. So 50 was the simplest, okay. Now, some part of my career I spent in quantum topology, trying to invent various invariants, and actually the talk is going to be invariants today of knots and three manifolds and so on. And quantum topologists usually stay in the area where it's, I mean, when they consider examples, they consider examples with very low number of crossings. We rarely venture in quantum topology beyond number 10. And their computers can compute this invariance with reasonable speed and so on. So if you heard about John's polynomial, that's a good example. But go figure, try to compute John's polynomial for this knot. I claim it's simply impossible in any practical sense. Why? Because first of all, number of knots grows hugely exponentially with number of crossings. Just from combinatorics of it, it's explosive. And also the way most of the quantum invariants are structured, their computation involves summing over certain intermediate channels per crossing or per piece of the knot, which is similar to crossing. And as a result, this also grows even for individual knot, the computation is highly exponential or hyper-exponential in this number of crossings. So unless something happens, some simplification, it basically explodes. So the barrier typically is around, I don't know, 12, 14, 16 crossings, somewhere there. That's where we can, in practice, do some computations, even with most powerful computers. So this basically brings an obvious question. So there are some potential counterexamples, interesting ones, to some of these conjectures, such as slice ribbon or smooth Poincare conjecture. But usually the examples even start at 50, 70 crossings, and they require going to hundreds. So how on earth are we going to bridge this gap? It's not an easy gap. It's not just to say, OK, let's wait a couple of years and things will improve. Because if you think about Moore's law, that computational power improves by, say, a factor of 2 every year or so, and this complexity of the computation, as I mentioned, also is exponential. Basically, we're plotting two exponential curves, or on a log scale, one against the other. So it means that if today we can do computation with, say, 15 crossing, it means that next year we can do 16. But if we need to move 50 crossings, we have to wait 50 years. And again, I don't know if I have that much time. So therefore, something else is needed, and this is a very serious question. This is basically what's keeping us away from solving some of these very serious problems. So coming back to the smooth Poincare conjecture in dimension 4, I said that if you find a pair of knots which share zero surgery, and one of which is sliced, the other is not sliced, you're done. So I explained all of these terms by now. Are there any questions? Yes.
Where does the idea of slice come
from? Idea of slice comes from, actually, that's been a while. So therefore, I'm not sure I can, I'm qualified to say it carefully. But for example, Seifert introduced the notion of analogous to sliceness in dimension 3. So Seifert surfaces play an important role. So each knot bounds a surface of a certain genus in 3 dimensions. And this is a much easier question compared to this. Sliceness is also part of a question, what is the in 4-dimensional ball? So even if it doesn't bound a disk, it may bound the surface of a certain genus. And these 2 questions, one addressed by Seifert surfaces, the other about sliceness in 4 dimensions, are kind of close cousins, the way they're formulated, but one is much harder than the other. But I think that's at least one way into asking. Sorry?
Hard to find slice knots in order to prove Poincare.
Yes, yeah.
You really embed this to do Poincare, to do surgery.
Yeah, so that was precisely the context here, indeed. So if you find slice disk for one, but the other is not sliced, then but they share a zero surgery, then you can glue them together. Yeah, there is a way to do it. Yeah. So any other questions? Did I answer this one? Okay, so yeah, going back to this theorem, so what do we need? So finding pairs which have same zero surgery is relatively easy. So there are millions and billions of such pairs. We can do it systematically because this is part of Kirby calculus. That's fast. So what we do need in this theorem is actually determining when something is sliced and when something is not sliced. So when something is not sliced, that can be determined by various abstractions. And again, here I don't intend to go through any of this invariants. So these are various invariants of knots, which are abstracting this property, yes or no property. And if you want to prove that something is not sliced, you just find that this invariant is non-zero. So the only thing I want you to take away from this list is that some of these invariants go back to late 60s, which is kind of early days of this subject. So the notion of sliceness was introduced by Ralph Fox and John Milner. These are some of the early works related to that. But many invariants, and actually the list could continue, come from recent years. So I want to point out that there is a huge gap here in terms of years regarding sliceness. And this is actually partly why I'm telling you the story, and this will be relevant for the future. So think about the gap. But this part is useful to abstract sliceness if you want to show that something is not sliced. If you want to show that something is sliced, then there is no easy way to do it because you basically have to exhibit this property. And it's very similar to showing that some complicated diagram is representing unknot. You just have to use certain moves to reduce it back to the, let's call it, trivial one. So in the sense of sliceness, technical way of formulating this would be to show that a given knot is concordant to the unknot by a certain sequence of moves. So this is hard, and again, complexity of this is enormous. So the only way I know how to approach this for complicated enough knots with up to 100 crossings is to use machine learning. So I'm not gonna spend much time in this talk on this subject, but for those of you who like machine learning, I want to point out that this is an interesting opportunity. And if you like to play with computers, go to our GitHub. You can download this code. Unlike DeepMind and many big corporations, we make it open source. You can play it with it yourself. It's easy to run on any laptop. And using this code, you can actually try to analyze sliceness for knots up to 100 crossings. So this is something I would never imagine doing myself in my old quantum topology days, but now with the help of machine learning, because it's just like teaching computer to play the game of chess. You can actually do it. And again, I encourage, if you're interested in topology, I encourage you to do it. So I think going back to this invariance, to invariance which obstructs sliceness, like I said, I'm not gonna spend too much time describing each one individually, but I want to point out or tell you where they come from and what is their nature and why there was this gap in development from late 60s to modern days. So part of the reason is that they require to think about invariants which are for knots of a slightly different nature, which invariants which are represented by spaces and where you have some maps between spaces. So you actually use homological algebra in a non-trivial way. And the invariants that I showed on the previous slide, they actually reside in various parts of spectral sequences, which operate on the so-called homological knot invariants. So these are not the usual knot invariants where you associate a number to a knot. This is kind of invariant where you associate to a given knot or given topological object whole complex of graded vector spaces and maps between them, so that you can again employ this package of homological algebra. And somewhere deep down there, deep in the spectral sequences, resides delicate abstraction to sliceness, something that knows about dimension 4. So this is actually interesting in its own right, because for many years, quantum topology had little to say about such interesting topological questions. And only in recent years, through the help of these homological invariants, we see the hope that quantum topology may shed light on questions like sliceness or some of these conjectures as SPC4 or slice ribbon conjecture. So therefore, in modern days, the invariants that we would like to construct, so now I'm again going back to attitude of trying to construct better, newer invariants. So we all have various versions of smartphone, and basically modern version or version, I don't know, 3.0 of invariants should be of this type, which associates vector spaces or homological invariants to knots, to 3 manifolds, and it would be naturally associating numbers to 4 manifolds. If you think about those of you who like TQFT, topological quantum field theory, this is basically asking for some TQFT-like structure in dimension 4, which would be associating, again, homological invariants to knots and 3 manifolds. But from that, we can infer some information about interesting questions in smooth 4 manifolds, in smoothly embedded surfaces in 4 manifolds, and so on and so forth. So questions, for example, about concordance that I mentioned briefly, sliceness, these are part of the same package. So this is basically the motivation for what one would like to do, and motivation why invariants of this particular kind, not just numbers, but homological invariants, are especially useful. So this is what I'll try to do in the remaining part of the talk and the second half, using geometry. So this was basically the formulation of kinds of problems which we would like to reach, and what kind of invariants we would like to construct. So next question is, where do we find them? How do we build this sort of invariance? That's not easy. So any questions about the first part? Okay, so then I'll go across the bridge. So this was discussion of topology, namely questions on low-dimensional topology that we would like to solve. So next part will be about geometry, and more precisely enumerative geometry, where again, name of Professor Yao will feature a lot in the form of Calabi-Yao's, and also, if time permits, I'll talk about our recent joint work, which aims to construct precisely this kind of homological invariance of three manifolds. So first, I'll start with something slightly easier. So if you try to construct some homological invariant of a three manifold, and again, we need more of those to answer interesting questions. So that's the goal. So first question is, what is the early characteristic? So can you construct, especially from quantum topology, for example, something like this? And that's the part which was work in progress with many collaborators, including recent work with Professor Yao and Ertan Shishmani that I'll come to later. But it started with joint work with Kumran Vafa, Dupay, Pavel Putrov, and many others about 5 or 10 years ago. And it goes by the name of this Z-hat invariance. Why Z has a hat is like for historical reasons. It's one of these things where the way things evolve is not necessarily most better motivated, or it's complicated discovery path that led to this very funny name. But never mind, it's basically meant to be early characteristic of this homological invariant that we need to construct. And that's something I'll talk about. Important point, of course, of this invariant is that here written as a graded Euler characteristic, so it's a doubly graded homology, and its graded Euler characteristic is an expression in Q, and the whole point is that coefficients in Q are integers. Well, simply because here there are coefficients of this graded homology groups. And this integrality is something that we've seen in many other areas of math. So now again, I'll jump to what seems at this point completely disjoint from my question about low-dimensional topology, namely questions in enumerative geometry. So enumerative geometry has all kinds of interesting invariants of Calabi-Yau threefolds and various variations, some of which we'll touch in a second, starting with Gromov-Witten invariance, which counts table maps from genus G surfaces into Calabi-Yau threefolds. This invariance, because they count stable maps, and maps may have stabilizers, are not necessarily integers. So these are in general rational numbers. However, in early days of the subject, it was noticed that you can repackage everything in terms of integers. And this is a very brief story for one particular Calabi-Yau, which is so-called local CP1. So it's a total space of O-1 plus O-1 bundle over CP1. And this is nice and toric. We have seen a couple of talks which include toric diagrams. So many people were developing computation, just practical computation of Gromov-Witten and other enumerative invariants for toric threefolds. So this is being the simplest, that's the toric diagram. And indeed, you can see that invariants are not integers, these are rational numbers. So here, genus is degree of the curve that you're trying to map in a Calabi-Yau. D is the degree, because our target contains CP1. So there are different number of times we can wind around that CP1, so that's the degree. And these are various benchmarks or breakthroughs in this computation that came essentially in 90s when the subject was highly fueled by questions of mirror symmetry, understanding of Calabi-Yaus, and so on. And one surprise from this perspective of this computation, so the way it's phrased here could be viewed as a computation in just algebraic geometry, essentially. But the output of this computation can be packaged in the form of Gromov-Witten prepotential, which is something we do naturally anyway because we want to organize things. And then one can notice that this actually has something to do with quantum topology. that once you do that, all these rational numbers, all the richness of these Bernoulli numbers that I had on the previous slide become Witten-Reshetikhin-Turai invariant of a three-sphere. So that's a very beautiful connection. So that's surprise number one. And surprise number two is that you can actually get rid of the rational numbers and phrase everything in terms of integers. So this was early days of Donaldson-Thomas invariants and various versions of thereof, as taught to us by Gukov and other people. The clue is to write everything in terms of variable q. So on the previous slide, we were doing expansion in genus and degree, and that's perfectly fine. But the variables that were counting genus and degree were naturally this h bar and so on. But if you write everything in terms of this q, and from the viewpoint of Witten-Reshetikhin-Turai invariant, we also want to repackage the rank. Say if you work with SLN, then instead of rank m, we would be working with variable a, which is q to the n. And that would be naturally associated to the degree in the Gromov-Witten prepotential. So there is a little bit of non-trivial dictionary involved, but once you know the dictionary, everything becomes beautiful. And you get two things at once. So you get, first of all, integrality, which was, remember, crucial to us if we want to discover some new kinds of invariants for low-dimensional topology. And secondly, you get a very nice relation between enumerative geometry and quantum topology in this case. Okay, that's pretty cool. So this is how I was pulled into the story. So what I reviewed for you was, in fact, before my time academically. So I was taught this by Professor Yao and Kumar Vafa. So for Professor Vafa, this was basically natural continuation of this story from 90s. Try to ask a similar question for more general three-manifold. So here you can ask, why is there a three-sphere appearing in this particular relation? And the reason is that the Calabi-Yau that we chose, this so-called resolved conifold, O-1 plus O-1 over P1, has non-trivial topology changing transition to yet another Calabi-Yau, which is the total space of cotangent bundle over S3. So these are seating as different components connected continuously in the space of Calabi-Yau metrics. So therefore, natural question that we were asking, and in particular, one of the questions that Kumar and Vafa posed to me when we were working together on this was how to generalize this to more general three-manifolds. So if you want a more general three-manifold, so first of all, it's easy to produce Calabi-Yau out of it. It may not have complete Calabi-Yau metric, but it's easy as a starting point. You just take total space of the cotangent bundle. Another thing that exists in this enumerative story and would be useful for us is open version, where we consider not just Calabi-Yaus, but pairs of Calabi-Yaus with Lagrangian manifolds. So they also featured in some of the talks, and particularly in lecture of Professor O. And they're quite standard in the package of Fukaya categories and enumerative geometry. These computations are usually harder because you have to count boarded Riemann surfaces mapped into your target or embedded into your target, where the boundary of Riemann surface lands on Lagrangian. So here, with this picture, what I'm trying to illustrate is that there is a three-manifold, which is zero section of this total space of our Calabi-Yau, and then there is a multiplicity n Lagrangian submanifold supported on the zero section. So this is a perfectly reasonable setup for sort of kind of local open Gromov-Witten count problem. And this problem is reasonably well defined, even from point of view of enumerative geometry. So we can start counting and ask a similar question, what the answer is going to look like. Even before doing any computation, you can expect that the answer will depend on a choice of three-manifold, because in this picture, everything is determined just by choice of three-manifold. So from this slide already, without continuing any further, it's clear that we're going to land in a world which associates to this counting problem something which is a three-manifold invariant. And that's indeed what the story is like. So first, you have to do the counting, assemble everything in this what people would call topological string partition function. That's physicist's name. Mathematics name for it would be open version of Gromov-Witten prepotential associated to this T star of M3 and some multiplicity and Lagrangian submanifold supported on the zero section. But the key point is that you would have to rewrite this answer not in terms of your usual genus and degree counting parameters, but convert everything in this variable q, which is related to h bar by this exponentiation map. And that's a typical step in relating Gromov-Witten and Donaldson-Thomas type calculation. So you would be trying to basically define this open Donaldson-Thomas type invariance, which in general is a very challenging problem. So this is something that I don't know how long it will take to develop. But what we want to propose is basically the answer to this problem in a particular case when Calabi-Yau is total space of the cotangent bundle to some three-manifold. So that's the context in which we claim that we have a proposal for solution of the problem. So that's the basically invariant I showed you before that I haven't defined yet. I'll define it in a second, but its enumerative meaning is meant to be exactly this resummation, or Borel resummation to be more precise, of open Gromov-Witten prepotential in this enumerative setting. So mathematically, therefore, it's a conjecture that what I'm going to show you on next slide can be basically viewed as a repackaging of open Gromov-Witten or Donaldson-Thomas type counting, where we have multiple Lagrangians and our stable maps from ordered Riemann surfaces land in Calabi-Yau with boundaries being on Lagrangians. Natural question then is, okay, so how do you define this invariant? And for this, I go back to our discussion of surgeries. So since everything is meant to be determined by choice of three-manifold, M3, and we already discussed that every three-manifold can be obtained by surgery on a knot or link, we can use this as a definition, and there is such a surgery definition of this invariant, for which you first have to construct invariant of a knot complement. So this will be some function, two-variable type function of x and q, which keeps track of some boundary data here encoded in the variable x. And once you perform the surgery, you basically get rid of this x. So this is what we're trying to do over this past years. And first step, this construction of the invariant for knot, or viewed as a knot or link complement, was actually mostly done by Sang-Yuk Park. So he was trained here in Korea, and currently he's transitioning to next chapter in his career of becoming assistant professor. So if you want to steal a very young, talented mathematician, so he's I would highly advocate for him. Starting with our work with Ciprian Manolescu, and then continued by Sang-Yuk Park and many others, now we have basically a technique to first construct mathematically well-defined series for, this invariant for complement of a knot or link. And then with Ciprian, we propose the surgery formula, which allows you to compute it for any three-manifold. And here is a particular surgery on a 10-crossing knot, for which you get some of this invariance. And like I mentioned before, in quantum topology, you're rarely able to do computations beyond 10 crossings. Very rarely you get beyond, 12 or 15 crossings. So part of the reason I'm putting this on a slide here is also to illustrate that this new invariant, which we are very excited about, is extremely well computable. Even though it's meant to be very powerful, it's actually fairly easy to work with. And as anticipated before, coefficients are integers. So you can see here lots of coefficients with plus, minus signs. So it's perfect for categorification being promoted to homology groups. So the state of the art of the subject is that there is a well-defined notion of this invariant for knots and links or complements of those, depending how you like to view it. Then you can actually apply the surgery formula to construct invariant of a three-manifold obtained by surgery. But this is an opportunity for young people to do some work, because currently there is no systematically well-written proof that this invariant is invariant under completely general Kirby moves. So what you can show is that if you have two links, framed links related by Kirby moves, then you produce well-defined, meaning invariant under isotopies and other things, invariance of the corresponding framed links. And then you can check that in each particular instance, you can verify that three-manifold invariant is well-defined, namely what you get is the same answer, but there is no general proof showing this in complete generality. So it's very similar to Sudoku puzzles, where you can easily check the answer. You can verify that this is kind of satisfies the right properties, but you don't have an overarching proof showing this in all instances. So there is a particular case if your framed link is so-called plumbed based on a graph, very much like in the previous talk, then actually in this class of manifolds, there is a general proof that it's invariant under Kirby moves, and the whole expression, everything that looked fairly complicated based on this quantum groups and so on, that I showed on previous slides, becomes a fairly simple, compact expression, which again is illustrating the point that it's easy to work and compute. So this invariant that I'm presenting is associating to three manifolds a Q series with integer coefficients. So this integrality is extremely important. It's the same integrality that was important in topology in the beginning, and it's the same integrality that we usually like in enumerative geometry when we relate, say, Gromov-Witten invariance to something integral. And it's meant to be, so here, the way I showed you the definition that we proposed and Sang-Uk Park developed further is based on quantum groups at generic Q. But this resulting invariant is kind of analog of four-manifold invariant, which also associates a Q series to a four-manifold and has been around for a while. So these two share some similar features. So first of all, they're both reasonably powerful, and you could argue that kind of hard to compute or interesting, although I try to explain that this three-manifold version is actually easier to compute and work with. They also have another interesting aspect shared between these two. So now I'm doing comparison between this four-manifold invariant and three-manifold invariant. That they happen to be characters of interesting vertex algebras. So it's in each case, you get an infinite Q series with integer coefficients. And this is exactly the property that characters of various VOAs have. So in both cases, there is a conjecture that for each given manifold, it's a character of a suitable VOA, and that's an interesting in its own right. And then in both cases, these invariants are labeled by some additional data, which actually I completely suppressed in the previous part, just not to clutter the discussion. But it's also an interesting aspect that there are these additional labels which were present in the previous slides. And therefore, these are not just invariants of a manifold, these are invariants of a manifold equipped with some additional structure. So let me use this last 5 minutes to say something about this invariant, namely Vafa-Witten invariant of four manifolds, especially given how close the two stories are to each other. And here, in this context, there is another opportunity to look for this homology groups for three manifolds as well, because this Vafa-Witten invariant is originally proposed through gauge theory. Its mathematical definition only exists for fairly limited class of four manifolds. In that sense, the three-dimensional story that I was showing earlier is a little better, in better shape, because it's defined in a much broader context. For four manifolds, again, this is ongoing program, and again, good opportunity for young people to work on to try to define it in larger context. Now it exists only for complex surfaces equipped with calorimetric, and many people have contributed to this development, including also work of Professor Yao and others. But since definition is aimed to be based on gauge theory, you can naturally ask what happens if you do this cutting and gluing that we always like to do in geometry and topology. Do you get any kind of Floer type homology associated to a three manifold? And that's exactly the question that Professor Yao, myself, and Artan Shishmani tried to ask in one of the recent papers. So in this 2 or 3 minutes, I'll try to tell you what kind of results we found and also conclude with open problems. Vafa-Witten theory is a very complicated gauge theory. So it's very much like Donaldson theory, which has only gauge connection as its basic ingredient. So then throughout the years, people studied many gauge theoretic problems. So here are only some of them. And as you can see, toward the bottom of the slide, as you read the slide, there are more and more ingredients. And this Vafa-Witten problem has lots of bells and whistles. So it's a pretty complicated gauge theory, but you can think of it as a beefed up version of Donaldson theory, which besides gauge connection has many other things. So as I said, we asked the question in this setup, what kind of Floer homology would you get? We cannot give you a more general answer, but we can give you an answer for particular family of three manifolds, which is of the form of a product of a circle and genus G surface, or more generally, some degree P bundle of a circle over genus G surface. Even this family is actually very useful for topology. So in particular, if we manage to compute Floer-like homology groups in this context, we can answer questions about the action of the Gleck twist or interesting surgery operations in dimension 4, and study various other questions. So the way we answer this problem is the following. In usual Floer theory, if you ask what is the usual Floer homology in Donaldson context is for manifolds of the form S1 cross sigma G, you find that it's related to quantum cohomology of the moduli space of bundles for complex group on this Riemann surface. So basically Riemann surface through its moduli spaces of G bundles determines the Floer groups. In the present case, this Vafa-Witten theory is especially nice, and I should point out that the computation is completely analogous to Kapustin-Witten theory. So in fact, our result applies to both, as we point out in the paper. So in this case, this additional ingredients, which besides gauge connection go into gauge theoretic definition, they make this problem especially nice in a way that instead of quantum cohomology, you get usual cohomology. So you would expect that instead of bond G, you may get something more complicated because your moduli spaces are much larger. Now we have more, besides the gauge connection, we have more ingredients, but instead of quantum, we'll have just the usual cohomology. So in that way, it's simpler. So all we have to do is to compute what the moduli space is. And this can be done following the footsteps of Nigel Hitchen, where he considered usual self-duality equations on a Riemann surface and found Higgs bundles in this way. I showed you that in the present context, we have, besides gauge connection, various other sections in this PD formulation of the problem. So you would expect that moduli space is much bigger. And indeed, it's the moduli space of so-called generalized Higgs bundles, where in the usual setting, the usual Higgs bundle is basically a single copy of this direct sum. It's basically a joint bundle of P tensored with some power of canonical bundle. And in this present setting of Vafa-Witten theory, we have 3 copies of this. So in other words, we have 3 Higgs fields in language of Nigel Hitchen. So it's much bigger moduli space. It's hugely non-compact. It shares many similar properties. In particular, it has a large group of symmetries acting on it, which just like for Nigel, simplified computation of topology of this moduli spaces. Same is true for us. So we could compute the cohomology, and that was basically how we determined these answers, and in particular answered questions about the Gluck twist and various other topological applications. I should say that for topology, this computation was mostly a negative result. It basically showed that this theory cannot detect the Gluck twist, but again, along the way, we produced lots of other results. So hopefully through this talk, I showed you many bridges across different domains. So I started my journey in low-dimensional topology and tried to advocate that we need new kind of invariants, which have integrality built in, and the level of knots or three manifolds would be naturally homological. And then I showed you a class of such manifolds associated either with quantum groups, a generic Q, or also coming from this gauge theoretic constructions. So this is only tiny slice of many bridges and domains that the subject touches upon. Briefly mentioned was applications to machine learning or even vertex algebras. And I want to conclude by once again thanking Professor Yao for teaching me how to transcend barriers and cross, and more importantly, build bridges. Thank you.